Welcome back. In the meantime, there is still an ongoing fierce battle in the Capture the Flag event. There are already 2 teams that have fully completed all of the tasks, but the final solution is yet not known, so who's going to conquer and lead the podium for the first 3 positions. So you still have some time left to complete all the tasks and submit all the flags. But in the meantime, while you are hacking your way through the CTF competition, welcome on stage Ēriks and Pēteris, who are going to talk about radio frequencies and Bluetooth. So welcome, guys.
Okay, so I'll start. I'm Pēteris Paikens, and my colleagues are Ēriks Dobelis. So we'll be talking about decoding Bluetooth from radio signal. So our agenda for today will quickly introduce why we care about this topic. Then we'll do a live demo of capturing Bluetooth data from radio, and a demonstration of sort of live coding session about decoding the physical layer of Bluetooth. And then, if we have time, we'll try to discuss shortly the impact of this approach, its limitations and consequences. So, yeah, this work is being done in University of Latvia Institute of Mathematics and Computer Science. We have a project on analyzing wearable device security, and in this context, we are sort of coming from the side of academia, trying to figure out ways how to analyze and improve security of wireless devices. So why Bluetooth? Why do we care? There are 3 main aspects why Bluetooth is relevant for such security research. So it's very widely used in many devices worldwide, and in terms of security, we care about those devices because many of them are sort of very personal devices which can be used to track and violate people's privacy by identifying the devices which are transmitting in our pockets. The second approach is that many of the wireless audio devices use Bluetooth, and they sometimes carry sensitive data. Your phone calls, if you have a hands-free device in your car, if you're using wireless headphones for a video conference, working from home. So this carries sensitive audio data. And the third sort of very interesting part with Bluetooth, that's more relevant for Bluetooth Low Energy, is keyboards. And again, the information on our keyboards transmitted wirelessly is quite interesting from a security perspective. And the second interesting aspect of Bluetooth is that it's a very, very complex protocol. Due to various historical reasons, compatibility with older devices, the need to be compatible with weak hardware, with cheap hardware, with old hardware that can't do much in the sense of, for example, encryption. The protocol is required to implement all kinds of sort of secondary features which violate its security in some aspects. And this has resulted in many interesting protocol-level vulnerabilities that are expected in a protocol of this nature. So, in terms of Bluetooth classic protocol stack illustrated here, sort of most of security research is focused on the upper half of this protocol stack in actual applications and data transmitted there. But for our purposes for this talk, we focus on the very bottom of this protocol stack, of the baseband, on Bluetooth radio, on the physical layer of Bluetooth. So why is that? So we feel that these layers are very underexplored from a security perspective. Because, well, we don't know why, but this is an obvious observation if you look at scientific literature, that perhaps it's because manipulating directly these baseband data in Bluetooth, it's quite inconvenient. And it used to require very expensive hardware. Now it requires hardware that's merely expensive. And some of the technical features of the Bluetooth physical layer makes it quite complicated to do experimentation analysis. And so probably because of this barrier of entry, security aspects which are kind of perhaps low-hanging fruit if you do analyze them, they have not been yet properly analyzed, solved, and fixed as it has been for other protocols. And the most Bluetooth security analysis like tools and software, they sort of work on this higher protocol level. They start with this host controller interface and then expect that the firmware or hardware of their Bluetooth chips will handle the baseband parts. But these Bluetooth devices do not expose the baseband protocols to the actual software that you can analyze. So obviously, all the other parts of Bluetooth have been found having interesting vulnerabilities, so why not baseband? There probably is something there, and we want to focus on exploring that. And to start with this, Ēriks will do a demo of capturing Bluetooth radio data.
Thank you, Pēteris. As Pēteris said, we are looking for a different way to capture the data which is traveling over the radio waves, and instead of using Bluetooth controller for around 10 euros, we have taken this device which costs around 1,000, and we will be recording directly radio waves and seeing what can we do with it. This exact device covers 56 megahertz bandwidth, so to cover the full Bluetooth spectrum, we would need 2 devices like that, which is still doable. This is not 100, this is just 2. But to capture some packets, we don't need to capture the data from the whole spectrum. It's enough that we take a couple of channels. If you have done some work with radio data, you probably know about the software which is called GNU Radio. For those who haven't, this is a software where you can graphically put together the processing blocks and do various calculations. So what I'm currently doing is capturing radio frequency. So currently on the screen you see frequencies from 2.445 gigahertz until 2.480 gigahertz. So this is the upper part of the Bluetooth and the lower part of the Bluetooth. What can you see on the screen? You can see on the right part you see those white lines. Those white lines is Wi-Fi, because Wi-Fi uses much wider channel. Bluetooth uses 1 megahertz for Bluetooth Classic and 2 megahertz for Bluetooth Low Energy. So you can visually distinguish Wi-Fi from Bluetooth. So where's the Bluetooth? So we will switch on my headphones and put on some music. Unfortunately, we will not let you hear the music, but you will see the radio waves. You see, I have started the music, and you can see one property of the Bluetooth protocol. It evades the channels which have high activity. So on the right part where you see the Wi-Fi is working, you don't see many of those small narrow lines, as it's automatically detecting that it's a busy space in radio frequencies. So you see those individual lines are roughly 1 megahertz wide, which is the width of the Bluetooth channel, and you see like they're randomly jumping for you, it seems, yeah. So let's do something different. So instead of music, I'll put music on hold, and I'll start something else. Now you see again those small narrow lines, but now you see there's a big difference, because you see them, there's the fewer of these lines, and now they go into the spectrum where the Wi-Fi is. So that's because I started scanning from my phone the Bluetooth devices around, and while scanning, the phone is sending out the packets, and during this process it ignores that the channel is already busy. That's why you see it overlapping with Wi-Fi. So what what can you do next with it? Yeah, so like looking at those pictures, that's interesting, but that doesn't give you information to work on further to get to the data which is transmitted, right? So what do we need to get the data? So one thing we need is to get individual channel. So I'm going back to my music. As you see, we have multiple channels here, and we need to look at the channels one by one. So with radio frequency signal, you can do things like filtering. You can do things like shifting frequencies using signal processing mathematics. So this is how filtering looks like. Yeah, I can filter out just one channel. It's not yet one, because I want to have the one which has more frequent data, like for this example. And then I can filter it down, and now I have selected just one channel. So what I can do, I can record the data from this just one channel and further process. Of course, I'm now showing the demonstration in some real-life processing. I wouldn't do it graphically, I would do it automatically, but this was just more visual. So I hope you can believe that I can record the data from this into a file. So let's switch to other processing environment. I'm using Python and then Jupyter Notebook to process this data. And this is a little code in my Jupyter Notebook, which is showing the activity of that specific channel. So you see that we have these bars. We have what we can see that there are higher bars, there are lower bars. So why are they higher and lower? Because I have put my headphones just near the antenna, and my phone is further away from antenna. So data from my phone in the radio data shows as much more quiet than the data from the headphones. As you can see, just taking one channel, and here's a recording of 4 seconds, it's still in just one single channel, multiple packets that we can see. So we can also zoom in and see that one of those bars looks like not exactly like a rectangle, but it has this lower part and it has this a little bit higher part. So let's move forward. So this one bar again, so I can now zoom closer in, and when you zoom closer you can see that it's just not one rectangle, it's actually two. So I think at this stage you can already guess that the stuff on the left is a packet from the phone, because it's further from antenna. You can distinguish that from the amplitude. And the packet on the right is the response from the headphones, which is higher just because it's closer in this case, and the power is let's say roughly similar. So on the left, one more thing you can see on the left is that there is an initial start in this packet which has more of this white stuff vertically, and then on further on there is more of the blue stuff. So why is this different? So why it looks like that? That's because Bluetooth is using different types of modulation. Bluetooth Classic is using 2 types of modulation, sometimes in one single packet. So the start of the packet is what is called GFSK modulation, and as this specific packet is enhanced data rate, it then changes modulation to DPSK to be able to transfer more data during the same time. So that's why this change in this visual aspect of the packet. The response from the headphone doesn't contain much data. It doesn't make sense to do all this complex stuff. It just sends in one modulation just a response that I have received the signal, so that's it. So not much else to do. So what else can we see from here? So Bluetooth transmits data packets on specific time slots. So how can we visualize it? So I have switched on lines which are exactly 625 microseconds apart. And you can see that the line where the first packet starts and when the second packet starts, it has integer count of these slots as an interval. So this is how Bluetooth works. On the even slots, the so-called central sense, and on the odd slots, so-called peripheral sense, it's data. So that's why it's so. Also, you can see that this packet is a 5-slot packet. Within Bluetooth, you have 3 types of lengths for packets. We have 1-slot packets, we have 3-slot packets, and we have 5-slot packets. So this is 5-slot packet from the phone and 1-slot packet in response. So you can see it doesn't take all the slots. It just takes the beginning as much as it needs. But that's 1-slot packet. It may not go into the next slot. So when we are automatically processing this, we can of course also automatically identify the borders of the signal. If you see I have switched on one switch, and it shows the beginning of each of those GFS key parts of the signal with violet and green lines. So if we would be automatically processing it, we would detecting signal at this width, and then we would process with the next step. So what do you do next? Many people still say we want to have like bits and bytes, not these fancy pictures with this blue stuff. Yeah, we don't have interest in these pictures. We are not artists. Yeah, so I am now selecting this this part from the signal, which is the start of the first packet from the phone. Just clicking save, and we can demodulate this signal using the same new radio. As you see, the process here is pretty simple. When you find out how to do it, then it's pretty simple. It's the main block here is this GFS key demodulation, which is supplied right by GNU Radio, and we just process this specific signal part through it. And you see the lower part on the screen. It shows ones and zeros that it spits out as the data that is contained within this radio signal. So now we have the bits. We have zeros and ones. So what's next? So next, as for any protocol, Bluetooth has defined, of course, the fields of the data transmission, and for Bluetooth overall, the idea is that it starts with so-called access code. Access code is a string of bits a string of bits that is easy for device to identify. So it's actually predictable data for the peripheral because it contains data which is containing the central address, which is by that time known for the peripheral if the connection is already established. So peripheral can identify this part of packet even if it hears it like with some interference and cannot demodulate it clearly, it still can pretty much guess it if it knows already the content. So that's how the peripheral device detects the start of the packet by this mechanism. Then it's followed by the header. The most important part of the header is type of the packet, because based on that you also know the length of the packet, etc. And of course it contains the address of the peripheral that central is communicating to, if we are speaking about the data from the central, as in this case. So it's also very important, like, to see like if it's for us or not. And then we have the payload, which can be 0 or can be much longer based on the packet type. The access code, as I said, is specially crafted for a device to be able to detect that it starts to transmit. One additional help in it is that it always starts with 1010 or 0101, depending on the next bit. And it ends with a trailer in most cases, which is also something similar. It is 1010, like, what a surprise, yeah? Or 00101. So what can we do is when we got those bits from the error, after demodulating them, we can just search for these bits, and when we find them, then we can like conclude that this is possibly a packet, and then we can do further steps on decoding and seeing what kind of data can we find here. So you see the raw data here. The raw data is containing just zeros and ones, the way it was received. Now we try to find this preamble and trailer, and based on that we determine like from which point we have to dissect further. And you see that in this case we have the access code, and correctly it's 1010. Then is access code. Part of the access code is MAC address part from the central device. In this case, it's also decoded already here as this string below. I could show you that my phone contains exactly these bytes as a part of its Bluetooth MAC address. And you see the trailer is also correct. It's also 1010, and all is fine. Yeah. So by that we can conclude that this looks like a Bluetooth packet, and we can work further on because it's really like seems like reliable case. Yeah. So what's next after this? After this access code, there is a header. So the header consists of the 3 bits of address, 4 bits of packet type, then there are 3 flags, and there is HEC, which is a sort of control that it has been received correctly. But there is a big but. Like first time you do, and this was my case. I would believe like 80% fall in the same trap. You see, oh, I have these bits. Like I did decode this access code, and now I know what is a packet type and so on. But no, there is a process in between. There is a process called whitening. So whitening is performed for the purpose of trying to make a number of ones and zeros similar to each other, because otherwise it's getting harder to demodulate. The demodulation is less reliable. So that's why it's whitened on the sending side and de-whitened on the receiving side. So let's de-whiten. So how do we de-whiten? Then comes the next problem. The whitening is dependent on the clock of the central. So the phone, like the Bluetooth chip in the phone, has a clock, which is specific for this Bluetooth communication, and it ticks. Like it ticks on its own. And how can we know, being on the receiver side, like how it ticks, like what's the current value? And the answer is that at this point, no, we cannot know it, because when they connect it to each other, they establish the current clock value. And from that moment, the peripheral knows and when follows the same clock by using its internal clock and seeing like what is the current value. What do we do now? So how can we circumvent it? So in this case, we do some brute forcing. We try all the possible values. Fortunately, there are only 6 bits for this clock. So there are 64 values for the clock at this moment. And we just try them all and see if one of the responses makes more sense than others. So in this case, we saw, oh, it's a 5-slot packet. So we can be pretty sure that the type of the packet is one of those which asks for 5 slots. So we have only 2 possible values for the packet type. So by that, we already extinguish majority of the other options. And we, in this case, I'm not going through the whole process here, but in this case, we got 4 alternative values for the clock, and we knew that it's one of them. So what can we do next? We still have 4, so we want to have 1, and we want to know which is the right one. So we take other packets, and as this clock ticks together with slots of the Bluetooth, we know that if the packet is sent 5 slots after, as in this case it was with headphones, we know that the clock is 5 ticks more. So we try again with a packet from the headphones, and then we see that this is a 1-slot packet. And again, we have limited us to specific types, which we see how many of the cases are still matching the situation. If not arriving to one single answer, we just take next packet. So in this case, we had to process 4 packets to be certain of the clock value, and from that moment we can synchronize all the processing and whiten all the headers. So next thing is this HEC, which is also additional control to verify that header was received correctly. And it's also based on seed value, and in this case the seed is not the clock. In this case the seed is part of the Bluetooth address of the phone, which was found out during the connection process, which we didn't see in our traffic yet. So what do? We brute force. So that's that's pretty easy. So once we know what is expected contents of the packet, we know that this HEC should match the situation, and we just find out which is part of the we find out this missing part of the MAC address. So by these steps, just from these radio waves, we could recover 4 bytes from the central's MAC address of its Bluetooth controller. So we have still 2 bytes missing, and those are 2 bytes which are part of that manufacturer's classifier. So essentially, if we have a vague guess what kind of device that is, then we can already determine. But but this is not so important for us in this case, because like for Bluetooth processing, we don't need that part of the Bluetooth address, but these 4 bytes are really essential for other things. For example, the frequency hopping. If we want to calculate the frequency hopping, we have to know this clock of the central and this lap part of the Bluetooth address. Without those, we can't calculate that. So that's why it is important. So this is how you work with this this kind of data. So I'll show you another picture. So maybe you now think that you have seen all, and you know how the Bluetooth signal looks like, yeah. But we just looked at a very specific case only. So just a moment.
Lots of analysis code there.
Yeah. I somehow miss one part.
Okay, so I can do a short overview of what we just saw, so some highlights there. So the key part of why this is necessary, so we are coming from a perspective of an attacker who does not know the actual device attributes, and see we are trying to sort of eavesdrop on someone else's communication. So the way Bluetooth is built, it relies on a bunch of pseudo-random values or kind of encryption or encoding mechanisms, which are there mostly for technical reasons to ensure that the signals are stable in the presence of noise or in the presence of some defective stuff. And and they establish these values during their handshake, which we can't reliably catch, especially if we don't have ability to catch all the channels at once. But as Ēriks just shown, we can start intercepting in the middle and make brute force attacks to obtain these parameters. Yeah.
Yeah. So I'm showing you next Bluetooth communication picture. So this initially looks very different, and when we zoom in, it still looks different. So you see that instead of multitude of these combinations of 2 peaks, one higher, one lower, this is like, seems like something is being communicated all the time, yeah? And then not at all. So let's zoom in. So what do we see zooming in? We see that it's not one big block, and we see it's a lot of individual signals. So this is how scanning looks like. So during scanning, the similar picture you would see in not all, but many channels. So the phone, in this case, is sending the inquiry packet, and it sends it with a certain interval. Yeah. So we thought we know the interval. So the interval here is a little bit different. You can see it on the time scale below. Sorry. Yeah, sorry, on this screen we have the samples there, not time. But this interval is exactly 10 milliseconds. So 10 milliseconds is matching exactly 16 slots. So it switches around channels. It sends inquiry packet on a channel, and switches to next channel, sends another inquiry packet, and so it switches around the set of channels and returns back to this one after 10 milliseconds exactly. And when we zoom out, we see that after some time, it completely changes the set of channels where it does it, and goes to next set of channels and then returns back. So in this way, it tries to cover like multiple channels, so that if the device has issues receiving it on one specific channel, for example, some very strong Wi-Fi sitting near that peripheral that we don't know of, but it's near to the peripheral, then we give the chance for the peripheral to hear our signal. So that's another example how Bluetooth communication looks like. Yeah. So I'm giving back word to Pēteris on making some conclusions and relation to our research, how this is useful for us.
Yeah. Okay. So as I sort of already interjected in the middle, so the goal of this sort of initial approach is to establish ways for extracting all this data to in a form that's usable for, let's say, people who want to work at a higher protocol level. And in essence, some Bluetooth hardware sort of tries to do that for a specific communication with a specific device, like taking the part of one device. But in this software-defined radio approach, we can capture packets from the air and try to see all the conversations that are happening right now in Bluetooth. Relevance to security of this. So this is not a finding of vulnerabilities. This is sort of basic research for the tools and methods which are required to explore these basic baseband level attacks. This brute forcing is sort of the first step of decoding the data we need to understand the packets we are seeing. It is also establishing the parameters which are needed if we would want to inject a fake packet. Like, it's sort of trivial to transmit random set of bits on a specific channel, but all these error codes which are based on device IDs and current clock value and the handshakes established during the initial communications, they make it quite difficult to know where you should transmit the packet in order for it to be received by some other device where you did not get this handshake. It's even difficult to predict which channel you need to send it to, because it hops every millisecond to a different set of 79 channels. So we are exploring the physical and baseband layer security aspects. Once we get this decoding done, there are also aspects for device fingerprinting. Like, some of these values are sort of just reliable from the specification, like 2 bytes from device ID. On the other hand, device behavior is sort of, in some sense, is underspecified. There are differences in how different Bluetooth devices try to do this scanning and inquiry process. Sort of, the specification says you should do this one way, but many devices don't follow the specification exactly, because they have figured out some 10 years later that if you do the channel hopping slightly differently, then you can do the handshake slightly faster. And, you know, consumers like headphones that join slightly faster. So we have like premium, and it doesn't mean a lack of quality. We have like premium devices from Apple which are intentionally breaking some parts of the specification, because if the other device is also an Apple device and it also knows the shortcut, then they can save some seconds of these handshakes. So these deviations from expected behavior are relevant for device fingerprinting based on just what we hear on the radio. The second part is why we care is we want to try to apply these hardware tools to eavesdrop and decrypt actual data. So this is a baseband layer. The packet payload then contains sort of all these higher levels of protocols which are being transmitted over Bluetooth. Like, it may be audio data, it may be keyboard key presses. So, this allows us to get these payload bits. And of course, for the security sensitive protocols, these bits are then maybe encrypted at some higher protocol level as well. However, we sort of have this unconfirmed expectation that many of these devices can't really do proper cryptography because of lack of randomness. So if you have, you know, cheap headphones, they try to make proper key exchange, key generation but if they don't have proper randomness, you can't do it securely. So we expect that even if they follow all the protocols, once we get to decoding this data, this encryption has a high chance of being compromised. And once we can do that, the same techniques and the same hardware, which allows us not only to receive packets but transmit them, they may allow either impersonation of devices after they've been turned off, or even man-in-the-middle attacks by relaying transmissions from another device in real time. So what are the big limitations and obstacles for this research? So as you saw, quite a lot of these tools were sort of ready-made, like these GNU radio components about basic radio stuff like the specific demodulation of channels. But quite a lot of the code shown by Ēriks is sort of written right here for this presentation, because the tool maturity is sort of lacking at this physical layer. There are a lot of tools which explore Bluetooth protocols above this baseband layer, but the publicly available stuff for analyzing this physical layer is quite lacking, and we sort of try to improve on that. And still we have this limitation that capturing all of the channels, like capturing all of the traffic, it requires to capture like all the 79 channels of Bluetooth, and it is still quite expensive in some ways. So it used to be that this required like devices which cost like $20,000. Now we can do it with devices that cost like $2,000, which is possible to do, but it's still a barrier of entry that sort of prevents many hobbyists from doing that. So there are software-defined radios on the price range of like 100, 200 euros. They can capture like part of the Bluetooth. You can capture like perhaps 1/4 of the packets. So for some attacks, capturing 1/4 of the packets is useful. For some, like eavesdropping, you really want to have all traffic, and then you need to do the integration of 4 devices or 8 devices, and it adds some technical complexity. Another limitation is that this processing, like we have shown the exploration of data, but some of the transformations that Ēriks sort of showed the results of, some of them require quite some computation time. Like if we capture all of the 79 channels and we want to do all of this processing for all of the channels, then we can't really do it on a laptop in real time. So there are some avenues of research of applying programmable gate arrays or GPUs to try and do it more effectively, but again, that's an interesting area of research, because as you saw in this packet where there was this sort of message from the phone to the headphones and the response. So the response came like, I don't know, 100 microseconds afterwards. So you don't really have a lot of time to respond. You really need to do it real time. So Bluetooth chips do it with specialized hardware, and which does only that. But if you want to do some interesting logic, like hacking in between, then all these timing differences become a bit problematic. And of course, finally, Bluetooth is a short-range technology. Like if I have some exploits that perhaps might crash your device by sending it malformed data on this baseband layer, I can't do it across the country. I need to, like, okay, Bluetooth might work across this hall with directional antenna perhaps twice as far, but not 10 times as far. So it still needs some physical proximity. Okay, and so why do we care about vulnerabilities in Bluetooth? So one aspect is that very many devices are affected. What we have seen in practice from higher protocol vulnerabilities, like there's Bracktooth and Swaintooth and some applications of that, is that when people have found vulnerability in a specific device, like, I don't know, a chip in headphones, it turns out the same vulnerability appears in some mobile phones and some other Internet of Things devices, because even if the devices are from a different vendor, using a different chip from a different manufacturer, all these manufacturers sort of share. They don't build their own code, they license code, or they license the code 10 years ago, and they have a copy which is sort of a fork of the code which is unmaintained and doesn't receive patches from the other manufacturer. So we have vulnerabilities which are shared across devices. And many of these devices can't be patched. Like, there is no way for my headphones to get firmware updates. There's just no functionality for that. And the final risk is that all the same Bluetooth chips are also used not only in like headphones and Internet of Things stuff, they are used on laptops and mobile phones. So if the traditional memory security model is, can I get the slides here? Shows the attacker can only attack the application through a sort of security boundary of firewalls, operating system security. In the Bluetooth, if you have an attack to the Bluetooth chip, then the Bluetooth chip generally has privileged access to system memory, which essentially bypasses all the operation system security fundamentally, because it's simply impossible to control on the hardware level. So that's it. Thank you for your attention, and we're ready for questions.
All right, thank you. Ready for questioning?
Yeah.
Absolutely.
Absolutely. By the way, if there are questions from the audience, please raise your hand, and the microphone will be delivered. Oh, you already have one. Okay, while you deliver the microphone, I'll ask my initial question. So, the first thing that Pēteris said on his summary is about the standards. How all open the standards are, how well actually they are implemented by the vendors. Are there any discrepancies? Does it actually make sense to reverse engineer the Bluetooth stack? Is it actually possible? Or you would have to do it for every single implementation, every single version?
Well, I'll probably take this question. So the standards are the specification of the standards is publicly available. However, what is interesting is that unlike other standards, like, I don't know, TCP/IP or other protocols, there is not a single reference implementation of these standards. So we have the specification, but every implementation, as far as we know, at least on the lower levels, it is like proprietary for the vendors, and so it can't really be tested or evaluated against the actual code.
And the specification is exactly 3,000 pages. And the language in it, like some parts, like these algorithms for this whitening algorithm, for example, I'm looking at the page, I'm reading it once, I'm reading it the second time, and after 10 times I get the idea what they thought about it. So it's not like written for, I don't know, software developer to go and implement it easily. Although I cannot say that information is not there, but it's really hard to chew. I
understand. So let's go with a question from the audience, please.
Yes, hi, and thank you for your presentation. I was wondering if there is there a best way to protect against this, against eavesdropping on Bluetooth? And also, especially if there is no way, should products start moving to perhaps Wi-Fi instead of Bluetooth for data transfer?
On eavesdropping, well, first of all, there's the radio part to eavesdropping. Yeah, so if somebody cannot hear the signal from your device, then they cannot do anything. So reduce the power of the signal, like build the walls around you, use smaller antennas, etc. So that limits reduces a little bit the risk. In essence, the standard is okay security-wise. The problem is with the implementation, and that's where we come in, because Bluetooth has two different schemes for encryption. So the second one is supposed to be secure still. The first one is supposed to be already broken. But if you have a chip which implements it in the wrong way, or we can force your chip not to use encryption, then you have the issues. I'm not sure whether Wi-Fi is anyway better than that. So you can, if you find vulnerability in the Wi-Fi implementation, like the same story repeats. So it's yeah, it's hard to compare. whether Wi-Fi is more secure. And for certain devices, you will never get Wi-Fi, because like the sensor type of devices, the wearable devices, they are definitely more interested in low power. So Wi-Fi is not low power by design. So that's why in some devices you will always have some sort of Bluetooth or other, let's say, protocol which is around low power.
All right.
Yeah. One more comment about this question is that you can assume that just as for TCP/IP, you can assume that your physical layer is simply insecure, transmitted in the open, even if there are some measures of security, and then you have to do your encryption on the protocol level, on the higher protocol stacks.
All right. So let's carry on. What do you before that? Oh, there are many questions. So hold on. Yeah. This is good that we're here. So you mentioned about also the you mentioned the example of not only reading the keyboard keystrokes but also trying to attempt. How hard would that be? Injecting the right frame, right command that would impersonate a keystroke on the Bluetooth keyboard?
That's I'm not sure. That's the honest answer. We should be able to, once we get all these parameters, we should be able to inject a Bluetooth packet which is sort of properly recognized. There are ways that, the protocol is supposed to protect against that. There are PIN codes for authenticating the device and so on. We suspect that these measures can be broken, but we don't have a proof of concept for that.
All right. I would say that if you get around the encryption part, or if the keyboard is using encryption in the first place, if it's safely implemented, etc., then it's hard. But if not, then it's certainly doable. It's certainly a direction within which we can work.
It may be that, for example, I don't know, Apple keyboards are secure, but some other manufacturer are not. Or other way, vice versa.
Yeah, we never know. But let's take the questions. I mean, the audience is raging for questions. There's one, and then we follow there. Mikko.
All right, thank you for the presentation. I have a really quick comment and then one question. So a quick comment about the history of Bluetooth protocol itself. I worked beforehand on the company who did also fuzzers for test Bluetooth, and it was really common that even with the valid cases which are specified in the protocol, you may crash the whole device. So in general, almost all the implementation were really poor, I would say. I'm not sure if that's the case anymore, but I would guess that
it is the case
for
this year's device as well. We have protocol level attacks this year, crashing many devices.
Yeah. So that's one thing. But I have a new big question for the radio part. I've tried to use the GNU radio 2 or 3 years ago last time, and it was always a hassle to get everything working. So do you have any good pointers where to start to get the instrumentation in a good level from the software point of view, and maybe some recommendations for the software radios also?
Mm-hmm. Yeah, absolutely. We went through this process ourselves. So first, starting from the hardware part, we were testing out different devices, and this is USRP B205 Mini.
From Ethos.
From Ethos Research, and I can definitely tell you that this is much more reliable than other options we tried. We tried HackerF, for example. With HackerF, for example, you have this weird problem that it's open hardware. That's why when you are buying it, you never know the quality. So that's disaster when you do the procurement, because you do the procurement, they offer the devices for the cheapest price. And then it comes out like it's performing much worse than you expected. And we need 4 devices, so we had 4 devices, and each of them was performing very differently than the others. And it's additional hassle to put it all together. So yeah, so if you can afford it, like this device is something I can already recommend. If you have more money, of course, buying more expensive device which covers the whole Bluetooth range at once is more convenient, but at the same time, with just 2 of these devices, you still cover the full spectrum, so it's not a big issue. About GNU Radio software, I absolutely agree that sometimes it's an issue. But there are good news. In 22.04 Ubuntu LTS, a nice version of radio, I would call it so, is included. And like half a year ago, I was like compiling all the time, and it takes like pretty significant time when you put together all the libraries. But now I'm just installing it from Ubuntu repository, and it is at least fine for my needs. Yeah, so of course you have to check the device support sometimes, etc. But yeah, now it's got more stable, I would say, on the software part.
All right, thank you. We will conclude the questioning session. So the ones who still have the questions, please do find these two young gentlemen afterwards.